The broadcast is now starting. All attendees are in listen-only mode.
Hello everybody and welcome to today's webinar. I'm joined by Shmuel Gershon and he works with Intel in Israel, and he is going to be presenting software. Well, it's complicated. And Shmuel has a history with EuroSTAR. He's been part of the program committee back in 2012 when in Amsterdam, I believe, when Zager was the program chair. He's presented at EuroSTAR. Even last year he has done a keynote, and we're delighted that he is going to be joining us again this year in Maastricht. And we're also delighted, of course, that he has taken time out to present this webinar. If you have any questions about this webinar, if you want to find out some more information, or if you want to give your feedback to Shmuel, you can do so over on Test Huddle. Shmuel has created a discussion there, and I'm going to share with you a link for this discussion. In your chat box now, you'll see a link, and that's where everyone's going to be heading directly after the webinar. So we hope to see you there. So I'm now going to hand you over to Shmuel. Hello, Shmuel.
Hello.
We're just going to open Shmuel's screen now, and he's going to take it from there.
Okay. So I'm on. Can you see my screen?
Yeah, we can see that.
Can you hear? Yeah.
We can hear you as well. Great.
Oh, okay. So exciting. Okay, that's great. So hello everyone, and welcome to this webinar on software and its complications. We will talk for the next 30 minutes or so, maybe a little bit more, about complex things and complex systems. Now, when a couple of months ago, Dara asked me to instruct a webinar about systems, and as I told him, that's pretty much like requesting a webinar about stuff. Right? Because what's a system? A system is a thing. Like any stuff is a system. Like we can define it better as a set of interacting or interdependent components forming an integrated whole. But the fact is that anything that has a relationship to another thing is a system. So we have a whole lot of types of systems that we talk, right? We are used to talk about software, but we have many. We have solar systems, and we have human organization systems. We have our computer systems, biological systems like the digestive ones, and not only computer system, but also microcomputing systems. And we also have a software system. Right? So it's software is just one example of a system. So talking about this, we exchanged some emails and what kind of stuff can I talk about stuff, right? And we decided that we can have a talk about how software systems are complex and why they are complex. One of the funny things is that after we set the webinar in the past weeks, the talk was advertised as the solution to system complexity. Right? It's within this webinar, Shmuel will show you how to deal with these tricky software systems. So the problem is that I don't have the solution. So I can imagine now people dropping from the webinar right away just because I said these words. But as I wrote in the real abstract, you can check it on the Test Huddle page. So it's all true. I will just tell you that it is complex, and then just despair and panic together with you online. Like as I wrote, you come with questions and you leave with more. What we'll do on during this time is that we'll have a conversation together about specific particularities of software that make it complex, more complex than we are many times used to imagine. And on this conversation, I will share with you two classic computer science papers that will help us understand why our work is so hard. For me, these are papers that I read when I started testing. Not only after I had many years working on software, but when I started testing, my universe expanded a bit, and these were, when I think about what what do I know or how do I think about systems, these two papers come in mind. So I'll share the content of them with you. Hopefully, this can be a good start to do this work of working with complex systems better, and a good start for us to better explain what we do to others, especially people that work together with us, like our managers. Like many times they think, how can it be so hard? So now maybe we'll have something to answer them. So why am I here speaking about this? Like, I'm a tester, I don't know, for 8-9 years. I was a programmer before. I've been using computers, I don't know, since I was a child, and today I work in embedded software or firmware as a technical person. I specialize on firmware, and I focus my work on tests that are tending towards the exploratory parts and towards the learning as you go, and note-taking. We have a previous webinar through EuroSTAR on note-taking. I have a wide range of things that I like. One thing that I am not is that I am not a systems expert. I don't also know what exactly would be experts on all systems. However, there are people who have some better grasp of special functions or special characteristics of systems. And I have been trying to learn from these people some of the interesting stuff. And to tell the truth, I do have about 36 years of experience with systems, like social systems and toy systems and any kind of system that we touch. And so do you. And not everyone has 36, but you've been seeing systems all around you since the time we were born. And it will be very useful for us to tap into that experience and that knowledge about how systems work when we, as we talk about software and any other system. So let's get back to the webinar. So it's a webinar about systems. And we said that we have all types of systems, like solar systems and organization systems, computer, biological, even software systems. And we have defined that anything, right, that has some interaction or relationship to another thing can be defined and described as a system. This is the definition straight from the Book of Books on Wikipedia. A system is a set of interacting and interdependent components forming an integrated whole. So it's one thing where you have different parts that one affect the other. Like these systems will have a common structure or a common behavior or a common purpose sometimes. Like they may have completely different structures and behavior but very similar purpose. They'll have a way where how they communicate, or specific instances where they do not communicate. I will just stop here. I received a red message from GoToWebinar that the experiencing network connection difficulties. Dara, can you hear all right?
Hi, Shmuel. Yes, I can hear you okay. There's a couple of attendees there who are having issues hearing what you're saying there. And just want to point out as well that we have this webinar is being recorded and will be available to view directly after the webinar. And apologies for the inconvenience. If you're using the web option, you can try switching over to the telephone option. That seems to have worked for some of our attendees. And just sorry again for this little setback.
Okay. Okay. So if my audio does get cut out or we have network issues like Dero, then just let me know.
No problem.
The good thing for people that are then switching to the phone is that we are just only starting now, so it's so you only missed a short introduction. So we're talking about like the systems that one thing that have many parts that either work together or have a similar or a common purpose, common structure, common connection. There is some effect in one of the parts onto the other. And once we understand that, we can see that everything can be viewed as analyzed as a system, or almost anything. And when you talk about a system, then many times you look at its parts as single parts and not system parts. But systems, they do get complex because one system contains systems, and one system is also contained in other systems. Let's take, for example, this motor vehicle, right? like we have in this picture. This is a system that includes a specific part, which is an engine. Now, an engine is also a system. We could now separate the system into the parts that interact within that. And every system, like our car there, the vehicle, is also considered a system for some higher level entities that includes other systems. Right? So cars are integrants of, I don't know, in this example, an urban locomotion systems. Cars are also parts of the car trade market, where people sell and buy cars. So you can have many systems that share a single entity. And this road or any urban locomotion system is also included in some larger system like traffic or traffic modeling systems that take into account all these different other roads. So that's when you look at a system, and when you have a palpable system like a car, a road, a tire, an engine, we easily can either imagine or look and point at the system and at the different parts of the system. But software, it's a little bit trickier. And here we'll start to talk about this topic of software, that software systems, they are complex. Okay, it will also be more useful that if I continue talking about a car or about solar systems or digestive systems. I don't know much about them. So it will be more entertaining if you talk about software. And what I would like to argue is that software systems are significantly more complex in their essence and in their nature than other systems that we are dealing with. And what's the reason for that? Why does that happen? First of all, it's because we can't really define what software is. And so if I asked you now, what is software? So is software the binary code that is compiled from a source code, right? And is this binary code, when it's in its electrical format inside the wires of our computer going inside our CPU and the main processing unit? Or it's the representation of this binary code in binary numbers or hex numbers? Would that be software? Would you say, oh yeah, that's what software is for me? It's the collections of highs and lows in electricity that move around. It doesn't feel like this is the software that we talk in our day-to-day, right? So what is software? Would that be a set of machine-readable instructions that direct a computer's processor to perform specific operations? That would be software, right? We can say, oh, independently of the representation, which is already something very dangerous to say, like I don't care how it's represented, but I can say independent of the representation in the real world, we can say that the software is the instructions that compose the actual software, right? A set of instructions. Now, Campaigner uses to say that this would be just like defining a house as a set of construction materials. Right? The house, it has an objective, a purpose, it has a feeling, it has a relationship to the people that uses that. So, like once together, these instructions of the software, they lose their identity or their individual essence as a jump instruction, a close instruction, and now they become something else. It's a system. So how do we define it, right? Or maybe we can forget about defining it and let's try to point at software. So everybody now just point at something that you would use to define software. Like point with your fingers. I am watching you now through your webcams. And I'm kidding, I'm not watching you through the webcam, but I hope you did this exercise of pointing at software, because it forces you to think together with me about what does software look like. And maybe you pointed at something that looks like this, right? So is that how software looks like? Like it's the graphical expression of a user interface? Is that software for us? So I don't think that's enough, right? We can try another visualization. When we have to draw software, like we are in a meeting with someone else and we have to draw the software, it ends up looking like the diagrams that you see on the screen. And then we can say that each diagram represents a software, or maybe but how come then these diagrams vary so much? And even the same diagram can vary between dates or between peoples or between purposes. You will change it. So it's a very fragile way to visualize software, right? And how many different ones you need in order to represent one single software in its entirety. So I think here too, we need some different visualization, and we can try to crowdsource the answer to this. Right? We can go to Google Images and write software and see what other pages or other things bring us when people write about software. What do we see there? Right? We are now, so in your screen you are now tapping into the collecting human trial of visualizing software, and you can see here a mix of computer hardware. You can see media used to transfer software from place to place. You can have you see some specific software or types of brand. So how does software look like? None of these look like software. Now, apparently, no one in the world has any other way to draw it or to visualize it. Right? This question is so hard that when the Computer History Museum wanted to demonstrate the Morris worm virus, like one of the first ones are very classic viruses that spread around in the internet. In fact, it's if I remember correctly, it started as an experiment in a university, and it just brought down systems all around the world. So they wanted to display the virus to the visitors, and the only way they figured out on how to showcase it was by displaying a diskette, a floppy disk. So that's the representation or the visualization of software. Now, for all the visitor know, the diskette can have the Morris worm virus, or it can have, maybe it's empty, or it may have the Frogger game. Right? it's all the same. So this visualization, it's too specific. It's too unspecific, right? For us to say, yeah, this is what I think of software. This is what software looks like. So we already can see something that is very special to software when comparing to other things that we are used to or other things that we engineer. Software, it's hard to describe. Software is hard to visualize. It's hard to point to. So this leads us to the central topic of the webinar, which is software is complex. And if software is complex, then testing software is complex too. You cannot control something complex without being dragged into the complexity together. And then to talk about this, I will bring then two friends, not so much friends, but two people that will help us understand these matters. One is Fred Brooks, and the other is David Parnass. Maybe I should call both of them doctors, so it's Dr. Fred Brooks and Dr. David Parnass. And they are two software scholars. Both they are active in software since the 60s and the 70s, and they are relatively influential. They were, and they still are, relatively influential in this world of software. They, as many other people who started together with the industry, they helped define this world that we now work on, and it's this world where we are able to do a webinar with software that runs from place to place. Now, Fred Brooks is famous for his papers and his books, like between them the paper, which is also the name of the book, called The Mythical Man Month, where he talks a lot about how do you organize teams and how do you manage the software creation process. You may have heard about the Mythical Man Month paper and book before. And David Parnass, sometimes I think less people have heard from him, but because he wrote a paper that is very specific about testing, for me it shaped the way I saw testing since the very beginning, and it may not have defined or shaped my views, but definitely defined my interest in the field. We'll see his paper in a minute, and you'll understand together with me how interesting it can be. So first, let's talk about software in general, and not specifically about the testing part. Fred Brooks wrote a paper called The Essence and Accidents of Software Engineering. The way it became known everywhere is that no silver bullet. He wrote a paper to explain the software is complex, right? And that this complexity, some of the difficulties of software and the hard properties of this software are part of the very essence and the very nature of software. And as such, right, there is no improvement or tool or solution or thing that we can do that can get rid from this complexity completely. That's why the paper is also called No Silver Bullet. Software has no silver bullet. There is no one solution that can suddenly make the creation and the testing of software simple. Like it says that software is complex and will remain complex until maybe we have a completely different concept of how software works. But now, and he says that the hard part about software, it's not in the things that we spend a lot of time on, like actually implementing or the software, but it's thinking about what we need to build and then figuring out ways to create that and figuring out ways to test that. Like the actual code part or the actual performance of a test, when you take it as the atomic part, just making operations or writing the code, it's not the hard part. So many times we try to solve this issue, the issue of complexity there. It's like, oh, writing software is complex, so now I'll bring a new IDE, like a new environment for writing code. Or oh, testing is very complex, so now I'll bring a new tool for managing the execution of the tests. But that's not where the complexity lies on. So it's you can bring a new tool, and you are still missing the solution for the hard part, because in his view, you cannot take this hard part out. Okay, so the main point there is that complexity in software is inherent to the software entity and cannot be solved or cured. Okay, so let's try. It may be a little bit hard to grasp at first, but I picked here from the paper. He brings many examples on why it's that way, and I picked 4 of them that I think will make it much clearer. So the first one is the inherent complexity of software. Like that software, it grows and it has, like any other system, many parts. And you can see here in the picture 2 examples of systems. One is the car, like we saw at the beginning, with its many parts, and the other is one representation of a software diagram. And one of the striking differences is that no parts in software is alike. Like you don't have parts that are just the repetition of the other part, or at least when software is well built, you try to avoid entire repetitions. And that causes that you cannot just take, in the car you have 4 tires, and so the 4 tires, they all behave the same. You don't need to create 4 tires. You don't need to test the 4 tires differently. Like they are systems that they share because they are the same. Then they share characteristics. In software, you don't have that. So any part of the software, it's different than other parts that you have in the software, and moreover, it's usually different than things that existed beforehand. Because in software, if it existed beforehand, you could just use something that was existent. And so this lack of repetition causes software complexity to grow in a nonlinear way as the size or the amount of things and parts that you have in software have. And even when you do have repetitions, then it may be even more dangerous, like because when we try to not repeat things unnecessarily inside software. So if there is repetition, it may mean that the software is poorly built. So it helps even less into solving or escaping from this complexity. So as software grows, then we get all the time newly invented parts and newly integrated parts that had nothing to do with what we had before. And nothing in the software that we use until now prepared us for this new thing, because it's a completely new thing every time. So this is something that you will see, I'm afraid to say only, because maybe there are other systems in the world that or other types of systems that work like this, but you will see it mainly on software. And it doesn't matter if the software is small or big, it's always the case, like that every part on the software is running differently than the other part. So, and apart from this inherent complexity, the software has what he calls an inherent conformity. So you have to compromise and to conform with a lot of things that happen outside your software, that they are forced onto us, and that they are also chosen completely arbitrarily without relation to the software. I'll try to explain that a bit again. Right? So in nature, so everything sets up neatly. Right? The relationship between different things, they may have evolved together. So many times things will just fit like a puzzle, right? Because I don't know, the world evolved all together, I think. But there's no such luck with software. When you are writing a software, you have a lot of constraints that are forced onto the people writing and testing software that were decidedly completely in an arbitrary form in relationship to the software. So you have to use frameworks, protocols, processes that were created with no relation to your product, but you have to comply with them. They are many times created in times where your software is not even existent. You don't control the entire environment where your software runs. And so you may have one design, one way that the team is modeling the way software works, but you have to make it fit with the models that teams all over the world, people writing the operating system, people creating the CPU, people creating the protocols that go before and the servers, and suddenly all these models of people deciding things independently one or the other, they have to fit. Right? And then that means that the end result is that you may have a nice like some nice ideas in your software, but you have to cut it and in a way that it will fit outside, and it becomes ugly, right? So the result is that we compared it with nature before, like that when we dissect nature and we are amazed at what you see, oh, it's so beautiful, but then we analyze software and we are horrified by what we see, right? That's a good phrase. I have taken note to tweet that afterward, right? We dissect nature and we are amazed, but we analyze software and we are horrified. Like and it may happen to a lot of people listening to this webinar. When you start to see how the software is created, you say, well, why and how come? And then you start hearing all the stories and what caused the software to be like this. Oh, now we had at the beginning, this is what we had, and you see there's a lot of constraints that happen many times for things that are out of control of the people creating the software. And this then makes software also complex by this very way on how it behaves and the way it on the world that software runs. A third point that Brooks brings is that inherent changeability. So differently than a blender, a toaster, or a decorative statue. Software can be changed after it is sold too. So it's not like you sell a software and now you start working on something else. The software will keep changing. And not only this causes endless updates, and I'm looking at you, Adobe Reader, but everything around the software, like from the hardware where software operates to the user that is operating the software, expect software to change to overcome known problems or new problems that were not existent when the software was created, and to adapt to new realities. So you create one software, and then you are forced to change it into something else later. And you cannot engineer a software the way you engineer a bridge, because the bridge is completed, and then we could say the bridge is completed when people start to use it, right? And then the engineers go to rest, and software is completed when people stop using it. I think it's an interesting distinction, and I hope it's a correct distinction, right? But you're never done creating the software until people stop using it. While in other types of products that we may be used to, you stop working on it when people start to use. He didn't say it this way, but I believe Fred Brooks will agree. And so this causes software to be different or more complex than other things that we are used to. Again, part of the nature of software. And another one that we saw earlier is the inherent invisibility. You cannot see software. You cannot point at software and discuss or improve. Software is created all in people's minds. So it's hard to find inconsistencies that way, because you have many people with different minds, all imagining the same software, and you cannot compare and see, oh, look, this is where it differs. So it's simpler to plan on finding consistencies in a machine than in software. In a machine, you can see that cogs don't match or that there's some noise happening, but software is intangible, and it's hard to compare different imaginations. And so these are four from the different examples that Fred Brooks brings there, 4 examples on why software is naturally and inherently complex in a way that you cannot change. On the other hand, he says that there are some complexities that you can change, things that are not related to software, but related to the way decisions that you take when creating it, or for example, tools. If you are using a bad tool to write your code, so you are writing your code on Notepad, it would just be unnecessarily complex when you could have it better in an IDE or some other system that has autocomplete or something like that. So to finish, we have to evolve this talk about software complexity into testing complexity. So we talked that complex software leads to testing being complex too. And here comes then Dr. David Parnass to help us understand a little bit of this testing part. Dr. Parnass, he wrote a paper called Software Aspects of Strategic Defense Systems. It's now known with the very cool name of Star Wars paper, because it was a paper written around and in relation to the Star Wars programs by the United States. We'll see it in a second. Some of the points that he brings in this paper is that software is unreliable on itself, and also because it is created imperfect. People writing software, they cannot keep up with the software as it evolves and grows. So you write one function and you remember it, and because you have only 3 variables, and then you write another 15 functions, and you think you are remembering everything because the computer is. Right? So the computer is very bad on imagining solutions, but once you write to him, I don't know, one number, it's much better than us in remembering. As humans, we can imagine solutions and create these solutions, but with time we get confused and we forget, and then we start working with other people, and now we have to match the things that we remember and things that we forget together with the things that other people remember and forget. And lastly, you cannot prove a software correct. You need something that is an empiric experiment. You need to actually run the software and perform tests on a live environment where you can learn from all the assumptions that you had and the things that you wanted to do and test. And this is especially interesting in the context of the Star Wars thing. So let me tell the story of the paper. In the end of the 70s, it was the big times of the Cold War, and the United States, they wanted to create the Star Wars systems, or a system for strategic defense, where they wanted to be protected from H-bombs, or nuclear bombs that sent to the United States from Russia. So they needed a system that would identify that something is coming onto the United States coast, and that this something is carrying or is threatening with an H-bomb, and then we'll just exterminate it or get rid of it, or solve the problem of this bomb coming on the system. And David was one of the people in charge of creating this system. And then he wrote this paper about how he does not agree to build the system because, in his opinion, this system could not be tested. Now, we as testers, we can understand that this is a very strong thing to say. Many of us are now just not believing that this can be the case. And it doesn't matter, right, if we agree with him or with not, but look about the things that it makes us think about. So he said that this system should not be created because A, the software could not be built well because of all the things you don't know, and because it could not be tested well. One of the important points here is that this system was defined as a one-off system. It happens one time, because if you don't, or let's take this picture, if you don't identify the bombs coming, then it's end of story. There's no need for the system anymore. Like you can fail only once, in the way at least that the Star Wars was defined or requested by the government. So he wrote there that a system that you have that works one time, it's very hard to test. It reminds me of there is this joke in which the husband brings a matches box home, and the wife says, "Hey dear, none of them work." And he answers, "How come? I tested each one of them at the store." Right? So it's you cannot test one match more than one time. And in this case, it's like the way that the system was being described and requested is that the system that is like a match. It has to work well in the first time that it happens in the field. So he writes that it's in prettier words than what I'm saying now. He writes that it's very complex, if not impossible, to have empiric or good empiric tests in a one-off system. And there are a lot of things that you cannot know that will happen during runtime. So, like how the targets will look like, what kind of decoys will be used, what kind of countermeasurements the enemy would be using, when it will happen. So, do we have 1 week to build it, or do we have more time? And a lot of questions like this. That because this was a high trust system, right? It's then you need real conditions to test it, and without trust enough, the system it would be like that. This is how it was defined. If it cannot be trusted, then it's useless. And the position there is that if you cannot test it empirically, then you cannot trust it to the level that the people commissioning the solution wants to trust it. So again, it doesn't matter the views that we have on how well it can be tested, but I think that it brings up a lot of interesting questions to us on whether such a system can exist, a system that cannot be tested to some or to which extent we can and cannot test our different testings. And this discussion brings us to some points that he also writes in his paper. That one of them is that programming is trial and error, right? So, and any one of you who has experience programming software or scripts or tools for testing, or has seen a programmer at work, then you see that they write something, and then they compile, and then they run, and then they change, and then they try again, and then they change until they get to something that looks like it could work enough to move to the next task. And so is testing. You try something, and then you see that it's not exactly what it doesn't answer the question that we were trying to answer, and then you try something else, and then you keep trying. So this trial and error, it works best when you can work on the entire system and have an empiric test. The idea here is that just like people writing software, they don't have an expectation of getting it right the first time, then the same thing for the testing. So I think if we take these principles together with the principles by Fred Brooks, we see that both of them give us some very good points on why do we feel so overwhelmed by software, even when it starts as something that's very simple and, oh yeah, I can test that and it will be, I don't know, a very basic thing. As soon as you start working on it, we see that it grows and grows and grows, and it's always more complex than what we imagined. And so here we have some points that will help us understand that. And even more importantly, it will help us make other people understand that, so they can work together with us better. And to end, then what can we do? So it's like I'm bringing here a very dark picture of, oh, software is complex and there's nothing you can do to it. And this is exactly what I'm saying. Like, you cannot remove software complexity. You can remove complexity if you remove a bit of software, right? If you diminish your software. So the right solution, in my view, is to embrace the complexity and adapt and accept it. So I know I don't bring a miraculous solution. There are plenty of consultants, especially tool vendors, that do bring some miraculous solution. Perhaps we should not believe them, or maybe we should send them this paper if they try to assert to us that, yes, whatever they are bringing us will solve the complexity problem and nothing will be complex anymore. And how do we do that? How do we accept and embrace this fact that software is so complex? First, we need to be aware. Right? If you are aware, if it doesn't surprise you all the time, oh my God, that's so complex, then you can work with that. You can discuss complexity, so it doesn't surprise anyone else in the team. It doesn't surprise your manager. It doesn't surprise people programming it. It doesn't surprise people expecting something else from software. People that try to compare and say, oh, but this is a smaller software, so it should be less complex than other software, and that's not true. And so you have to understand and talk about the parts and the relationship between the parts of this software that you have. Now, one solution that can help you reduce complexity is look for incidental complexity, things that are not in the essence of the software. Many of the things that we decide when we create software, when we test software, are not in the nature of software, but it's just the way we organize our teams and the human interactions that we have, the interfaces that we have with other teams or users or other companies, technologies that we decide to use, the way we design our solution. So there is some complexity that we can remove. Software will still be complex, but at least you have taken unnecessary complexity out. Try to remember that that example on, like, you can say, well, if a tool will not help, then I will program on a pen and paper. No, it will be more complex than, or at least the act of writing the program will be more complex than writing it somewhere else. As long as you know that you are removing complexity that is attached to software, but not removing complexity of software, that's good. Like, you have to be aware and conscious of what exactly is the process that you are doing there. And I write it here because that's mainly the first solution that comes to people when you talk about complexity, which is modeling. Now, modeling is good because when you model, you divide things in parts and you understand relationships. You have to be aware because all models, like, no model is complete, every model lies, and things like that. But models are very useful. In fact, Parnas, in a different paper, he has this a suggestion, or like he says that he seldomly sees a model that is useful as a description, because it's lacking things, but you can use models to raise questions, options, and understanding about software. So if you want to bring up a lot of questions and have people talk about the software, then go and make a diagram. Now, don't think at the end that this diagram is really representing the software that you created. And so these are my small suggestions on what can you do. The big suggestion is just know about this and talk about this with other people, so no one is surprised about software being complex. And if you want to hear more about what Dr. Brooks and Dr. Parnas said 30 years ago about software complexities, then you can read their papers here. Now we have about 10-15 minutes to the end, and this is what I have, so you can ask now questions. Probably there are collected questions as we went, and we can continue on the Test Huddle forum too.
Thank you very much, Shmuel, for that webinar. I'm just going to open up my screen here again, just go through a couple of slides before we head across. And you can all see my screen again there now. So we're delighted that Shmuel has taken the time out to host this webinar, and he's also going to be presenting 2 different sessions at EuroSTAR this year. The first one here is on Wednesday the 4th, demystifying embedded software, and there's another session then as well on Thursday the 5th, inside a tester's mind, focusing and defocusing. I'm just wondering, Shmuel, if you could maybe give our attendees today a little insight into what they could expect from your sessions here. Maybe start with the first one there, demystifying embedded software.
Yes, yeah, I can talk shortly. So the first one is an introduction to firmware and embedded software. Many people think that it's something special or something very different than the software that runs on desktop. And in this talk, I explain a little bit of what is embedded software and some examples of things that testing embedded software brings. And I also explain how it is actually very similar to other things that testers of software are used to, and no one needs to be afraid of it. So,
great.
And the second one is this is a tutorial, so it's a longer session. I think it's not at 12 but at 2 afternoon, and so it's interactive. It has a little bit of theory and talking, but it has also some exercises especially built for focusing and defocusing and on the 2 different types of mindsets that we testers can nurture.
Okay. Now we've had our Best of EuroSTAR series, and we've had an Agile series, and next month we're going to have another webinar series called the Mobile Webinar Series. And during this webinar series, we will hear from Aaron Krunsbrunner. He will be doing a webinar on continuous quality as a key for 5-star mobile app delivery. We have Stephen Janaway, who is presenter at EuroSTAR. He's also going to be presenting at the Mobile Deep Dive event, which will be taking place on the Friday of EuroSTAR. And he's going to be doing a webinar called The Mobile Tester, A Place in the Team. And we're going to wrap up the series with the webinar from John Harger. And his webinar then is going to be on mobile app test attacks to efficiently explore software. And if you want to find out more about these sessions, just go to testhuddle.com/mobile. And this coming Friday is the deadline for our EuroSTAR Super Early Bird discount, where you can save up to €430 on your ticket. So if you want to make the biggest savings you can for the conference, I recommend booking your place before Friday, and you can attend those two amazing sessions that Shmuel will be presenting, along with many other. And we also have some great social events in the Chateau near Cannes. And we also have a conference party in La Caverne. If you want to know a bit more about these venues, just check out the EuroSTAR website, look up the social events. And as well, I want to point out that you can make even bigger savings too when you register a group of 4 people. On the Friday of EuroSTAR, we have a brand new mobile testing event called Mobile Deep Dive. And if you're attending the full EuroSTAR conference, you can avail of the 50% discount on your deep dive ticket. More details on that can be found on the EuroSTAR website. Finally, I want to just remind everyone that we're going to head across to Test Huddle for your questions and discussion. I'm going to share with you again the link, and in your chat box there's a link there that will bring you into this discussion. I want to thank Shmuel for the webinar, and I want to thank all of you attendees for coming along. We hope to see you at future webinars. And to sign up to other webinars, just check out the webinar calendar that's on Test Huddle, and we'll see you then. So we're going to head across now to Test Huddle. Take care and goodbye.
Goodbye. Thank you all.